Okay, so we're on section 4.6, stoichiometry in the real world. If you take a look at the warm-up, they've given you some ingredients to make ice cream sundaes. And so it says, suppose you're working in an ice cream shop. A group of customers come in. They would like to order ice cream sundaes. The shop's computer page reads as follows for ice cream sundaes. So you have the sundae ingredients, you have the number of items in the sundae recipe. What's the maximum number of sundaes that you can make for customers? Well, think about it in terms of, like, what are you going to run out of? Chocolate what? Chocolate syrup. You can only do it 4 times. So how many sundaes could you make?
4.
4. Okay. What item limits the number of sundaes you can make? Chocolate syrup. How much of each of the excess items will still be left as sundae stock? 2 scoops of ice cream and
then
471 cherries. Okay, so when we relate this to chemistry, if I've got so many reactants and I'm making products, one of my reactants will limit how much product I can make. And we would call that the limiting reactant. Sometimes they call it the limiting reagent. The limiting reactant produces the least amount of product. So that least amount of product is also known as the theoretical yield. Okay, theoretically it's how much I should make. It's often calculated. Okay? All right, so what we're going to do is we're going to take a look at the quick check, because the quick check does a really good example of sort of introducing this concept of limiting reactants. So if you take a look, it says, consider the following situation. You have 2 carbon monoxide molecules plus 1 oxygen molecule producing 2 carbon dioxide molecules. And then they told you underneath in a box that you've got a couple of things here. Let me just draw these really quick. Here are your 3 oxygen molecules that you have available. And then you have 4 carbon monoxide molecules available. So using this information, which reactant is in excess? Oxygen, because for every 2 carbon monoxide, it combines with 1 of these oxygen, right? So these would come together to make a carbon dioxide molecule. And then these would come together to form another. So I'm left over with 1 O2. Okay, so the reactant in excess is O2. Sketch any remaining reactants and products to show what will be present once the reaction is complete. Well, once the reaction is complete, this is what you will have left over, right? 1 O2. Okay. How many carbon dioxide particles are formed? 2, right? And how many excess reactant particles remain? 1. Okay, so what we're going to do is we're going to incorporate this into some actual math problems. So what I want you to do is take a look at the practice problem set on limiting and excess stoichiometry. Okay, we're just going to take a look at problem number 3. Okay, problem number 3 says when ammonia is passed over hot calcium. So ammonia is NH3 and it's going over hot calcium. Calcium hydride, which is CaH2, is produced, and so is nitrogen gas. What mass of calcium hydride, so I'm going to put question mark grams underneath CaH2, results when 20 liters of ammonia measured at STP and 150 grams of calcium reacted? What quantity of excess reactant remains? So I just need to put some coefficients in here to make sure that this is balanced. Okay, and now we're ready to go. So let me explain this whole concept of limiting reactant problems. You need to know how to recognize a limiting reactant problem because they don't always tell you. Okay? How do you do that? Well, they give you the quantities of two reactants. That's how you know it's limiting reactant problem. Okay? That means you have to do double the work. You have to figure out which reactant produces the least amount of product. Okay? So we're going to do that now. So I'm going to go ahead and start with NH3. If I'm at STP, can't I take 20 liters of NH3 and divide it by 22.4? Isn't this just sort of like a rule for when we're at STP? I can convert liters to moles using this. And then make sure you include what substance you're working with because we need to convert that substance to calcium hydride because we need to figure out how much it would produce. So I have a coefficient of 2 there, so it comes here. I have 2 moles of NH3, and then I have 3 moles of calcium hydride. And then we want to go to grams. So I'm going to put the molar mass of calcium hydride here. Okay? The molar mass of calcium hydride is 42.10. That comes from the periodic table. Calcium is what? 40.08, I believe, plus 2.02 for hydrogen. Okay? All right, you're going to multiply and divide all of this out. That's going to give you 56 grams of calcium hydride. Okay? Does that make sense for the first reactant? All right, now you have to do the same thing with the second reactant. So we're going to take 150 grams of calcium, and we're going to convert that to moles by dividing by the molar mass. Then you have to use the coefficients. I have a 3 in front of calcium, and then you have a 3 in front of calcium hydride. And then we need to convert that to grams of calcium hydride. The molar mass is 42.10. You're going to multiply and divide all of this out. That's going to give you 158 grams of calcium hydride. You may want to double check my math. Okay? Okay, now that I have this, listen to me carefully. Look for the lowest amount of product that was formed. Wouldn't that be 56 grams? 56 is less than 158. Okay, the lowest amount of product that was formed is called the theoretical yield. This is important for doing something later, okay? But the theoretical yield, when you're doing limiting reactant problems, is the maximum amount of product you can make. Because what will happen is you will run out of NH3 before you can make any more. So NH3 is your limiting reactant. The limiting reactant makes the least amount of product, but sometimes they phrase it as the maximum amount of product because you will run out of NH3 before you can make any more. Okay? Okay, so that's how you do limiting reactant problems. Not that bad, right? Okay, now we're skipping percentage purity and we're going straight to percent yield. Okay? So percent yield, can I erase this? Yeah. Percent yield is the actual yield, so this is what you actually made in the lab, and they'll sometimes tell you in a problem how much was produced, divided by the theoretical yield times 100. I often have students get confused when we multiply by 100. They think they have to move the decimal over and multiply by 1, or they move it to the right. They don't understand. So when you multiply by 100, that means your final result here will have a unit of percent. Okay, because the units on the actual yield and theoretical yield will cancel. If they're grams, if they're moles, it doesn't matter. They'll be gone. Okay? So what we should do is take a look at the practice problems on percent yield. So why don't we take a look at practice problem number 1. Practice problem number 1 says we have a chunk of zinc metal and it's reacting with excess hydrochloric acid. This is a single replacement reaction. You're going to spit out hydrogen and zinc chloride. And then if you balance it, you would put a 2 in front of HCl, and that's it. Okay, so this is my balanced reaction. What is the percent yield if a 7.23 gram sample of zinc produces 2.16 liters of hydrogen gas at STP? Begin with the balanced equation. Okay. They told us the actual yield in the problem. If you go back and you read it carefully, this right here is your actual yield. Okay? That's how much they made. We don't know the theoretical yield, right? Because you calculate the theoretical yield with the reactant that they gave you. So we're going to take 7.23 grams of zinc. We're going to divide that by the molar mass. Molar mass of zinc is 65.38. And then you have a 1 in front of zinc. And then you have a 1 in front of H2. And then since we're at STP, I can convert this to liters. Okay, so you're going to multiply and divide everything all the way across. That's going to give you 2.48 liters of H2. Okay, and this quantity that I just calculated is my theoretical yield. That's how much I should make when I do it myself. Okay, whether you make that or not is a different story. Okay, now we're going to calculate the percent yield. So if you want the percent yield, it's going to be the actual, which is 2.16 liters, divided by 2.48 liters, my theoretical yield, times 100. Liters will cancel there, but you're going to end up with percent as your unit. When you divide those two numbers out, you're going to get 87.1. And that's it.